Good afternoon, Physics 30. I hope you guys are having a wonderful day today. It's a lovely, windy August day. Today, well, when I'm filming, today we're going to be looking at elastic and inelastic collisions. So please enjoy the pun. It's great. Awesome meme. It's good. Today is all about physics puns. I'm even wearing a physics pun. My shirt says, atoms make us all matter. I thought that was very appropriate. Atoms make us all matter. Matter. Had to happen. All right. So today with the elastic and inelastic collisions, this is the last lesson of the unit. So once again, it's August. I don't know exactly what's going to be happening when we get back to school. If we are still in class, you have a unit test coming up at the end of this, and your unit assignment is going to be due ASAP. So see me in human form to figure out when these due dates are and test dates are. So last topic of the unit. So ladies and gentlemen, elastic and inelastic collisions is another extension of your conservation of momentum. So we've already talked about linear conservation of momentum and 2D conservation of momentum. Now, in all of the collisions that we are going to be looking at in our isolated system, momentum is conserved in them all. It doesn't matter what scenario you're in other than isolated system, momentum is conserved. So, however, elastic or inelastic collisions are going to be based on whether the total kinetic energy is conserved or not in that scenario. So we're going to talk about elastic collisions first. These elastic collisions, when the total kinetic energy in the system is conserved. So what that means, the kinetic energy of the objects prior to the collision is going to be the same as the kinetic energy of the objects after the collision. Okay? So your the sum of all kinetic energy prior to the scenario is going to equal the sum of all the kinetic energy after the scenario. So your prime. Or you could also write it in that fashion. Now, I'm pretty certain this is not, those are not on your data sheet, so you just need to know this concept. There's nothing on your data sheet for you there. Sorry, guys. The data sheet we're using is the same one you're going to get in your diploma exam. So if it's not on the data sheet, you need to know it for your diploma. Or you need to memorize it for your diploma. That's a better way to word it. Okay. Inelastic collisions occur when kinetic energy is not conserved. So your EK, the sum of all EK prior, is not going to equal the sum of all EK after the collision. Okay? Now, remember, where is this energy lost? Well, are we following the law of conservation of energy? Of course! We always got to follow the law of conservation of energy. The kinetic energy is, quotes, lost because the energy is transferred into the bending and crumpling of anything in the collision or any deformation. You could also get things like sound energy. That's a type of energy. Heat, okay? All collisions at a macroscopic level are going to be considered inelastic. So lesson subtle hint, you need to know that. All elastic collisions, they don't really occur much in reality except at the subatomic level. So protons, electrons, and neutrons crashing into each other. That's really the only time that we are going to be seeing things that are going to be elastic. You may see questions involving atoms that are going to be an elastic collision. But as soon as you get past an atom, you're not going to see elastic collisions. You're going to see inelastic collisions. Okay? Okay. So, ladies and gentlemen, you need to know those things. Know when you're going to see inelastic collisions and when you're going to see elastic. Okay? Okay. So what we've got is we've already talked about this briefly, how the law of conservation of energy still applies in inelastic collisions, because it just means keyword kinetic energies are not conserved. The sum of all energies in that system are still going to be maintained, but the energies are just going to be converted into other forms. Cool beans? Cool beans. Now, momentum is still conserved in both elastic and inelastic collisions, okay? The term elastic and inelastic strictly relates to kinetic energy, nothing else in that system. Cool? Cool. All right. So let us jump over and do a bit of math, ladies and gentlemen, to look at the sum of the ideas of the kinds of questions that you're going to have when it comes to your equations for elastic and inelastic collisions. So, an argon atom with a mass of 6.63 times 10 to the power negative 26 kilograms travels at 17 meters per second right and strikes another identical argon atom dead center traveling 20 meters per second left. The first atom rebounds at 20 meters per second left, while the second atom moves at 17 meters per second right. Determine the collision before and after, or determine if it's elastic or inelastic. Well, ladies and gentlemen, if you have already observed the pattern and can think about where we're going here, you might already be able to quickly determine your answer. So if you can, awesome. Well, let's set up a diagram here. So we've got one moving right at 17 meters per second. The mass of both of these is 6.63 times 10 to the power of negative 26. It's the mass of both. Well, this guy going right is 17 meters per second, and this guy right and this guy going left is going to be going at 20 meters per second, and that's 1 and 2. Afterwards, it reverses. So that is before. This is after. There's then 1 and then 2 after the collision. The masses of each of them is still the same. Well, in this case, the V1 prime is 17 meters per second, and V2 prime is, oops, I have them backwards. I beg pardon. Can't even say it's Monday because it's Saturday. Okay, so this one is 20 and this other one is 17. Okay. Now, remembering, ladies and gentlemen, that when we are going to be dealing with kinetic energy, we are dealing with scalar quantities because EK equals 1/2 mv squared. That V is speed, not velocity. So the direction is not going to play a role in our calculations here. So let's see if these guys actually match. So your EK initial and EK prime. Let's see if these are going to work out here. Now, there's a couple of different ways in which you can go about this. The first is we need to set up our scenario because we are looking at the sum of our kinetic energies, ladies and gentlemen. So, well, here is object or mass of 1. There's mass of 2. And 1/2 mv squared of atom 2. So there's a couple of different ways that we can go about this. Okay. First, I'm going to choose the most mathematically straightforward way we can go about this. That means we're going to be doing lots of canceling because we got a lot of similarities here. So, ladies and gentlemen, let us math. Now, that 1/2 m, what can I do with it? On both sides. I can factor it out. It's the same value. So I can absolutely factor out 1/2 m on this side and have my v1 squared plus my v2 squared. You're going to get that exact same value. It's in both terms on both sides. So I am going to factor out on both sides. Okay? So it is mathematically the most straightforward way to do this, because guess what now you can do? Now what? Cancel it. The m is the same. These atoms are identical. Because n is the same value, I can cancel out 1/2 m. They are the same numbers on both sides of the equation. So mathematically, they can cancel. So I am left with v squared 1 plus v squared 2. That is going to equal my v1 squared prime, there we go, plus v2 prime squared. There we go. That's not up to the power of 12, guys. That's prime. I'm just going to get rid of the primes just for the sake of this, because it's a mess. So I can bracket them. You know what? We'll bracket. There we go. I'll bracket and put my primes. There we go. So now what I'm going to do is put my numbers in. So my first V1 is 17 meters per second. I square that. And I put my next one of 20. I square that. I am going to then put my 20 and square that, plus 17 and square that. I think you can see where this is going, ladies and gentlemen. So once you solve for this on both sides of your equation, you're going to get the lovely number of 689. On this side, funnily enough, you're going to get 689. So ladies and gentlemen, because I canceled out that 1/2 m, this number now is not the EK. But does it matter? No, it doesn't matter. We just need the numbers to be the same. We got rid of the 1/2 m on both sides because it's the same value. It's no longer the EK. That's one way to solve this equation. If you want, you could actually multiply each of the v's by their appropriate, or v squareds by the appropriate 1/2 m, and actually find the EK. But in this case, you haven't been asked to say, what is the kinetic energy? You have been asked, is this elastic or inelastic? So what is it, ladies and gentlemen? Elastic. Okay, so because these two values equal, it is therefore, and it would help if I wouldn't drop that extra E in there. It is therefore an elastic collision. In theory, this also makes sense because we're dealing with atoms. So the second you get a scenario that is not going to be an atom, what's it going to be? Inelastic. So there is a whole spiel here. This next question is a massive spiel here about billiard balls and their speed before, their speed after, etc., etc. Tons and tons and tons of info, which absolutely we can get you to do a 2D conservation of momentum question on. But that's not the point for this particular video lesson. Today's elastic or inelastic. Well, just for what you need to know is this massive question is dealing with bowling balls. The white bowling balls, billiard balls, okay, pool balls. So the white ball, green ball collision is classified as what? What's your best answer here? What do you guys say? Our best answer is going to be inelastic. So we know for sure that we don't have enough data to truly say, is this going to be an isolated or a non-isolated system? They haven't really told us that much. We assume we're dealing with isolated, but we haven't been told about that. The best way answer for this question is going to be inelastic. Why? Because we're dealing with pool balls. We're not dealing with atoms, ladies and gentlemen. So, and honestly, if you sit down and do the math for that question, you are absolutely going to see it's not going to be an elastic collision. You're going to get the EK on one side not equating the EK on the other. Okay. Another way to look at this, and honestly, this question number 3 is a way better way to classify this question, and it's the standard diploma exam chart question. I would expect on anything I will give you or anything the diploma will give you, it'll be a question that looks like this. Now, what we've got, the collision of the white ball, green ball is classified as blank because of blank is conserved. Okay. We have, now with the column questions on your diploma, this is the key. So you are going to cover, pick a column. I want to pick the column first, this one here. Well, guess what? I've got 2 choices. I've got elastic and I've got inelastic. Well, because we are dealing with billiard balls, what are we dealing with? What type of scenario? Inelastic. We're not dealing with atoms, so therefore it is not going to be elastic. Cross off A and B. You narrowed it down to 50-50, ladies and gentlemen. Now, because what? Because blank conserved. We have momentum is not, or kinetic energy is not. Well, we know that momentum is conserved because momentum will be conserved in all systems that we're going to be looking at in Physics 30. They are going to be your, what do you call them? Isolated system equations, okay? Going to be an isolated system. So that means that we are going to have momentum conserved. Whoops. So, eraser. There we go. So that means momentum is going to be conserved. Cross off C because momentum is conserved. That's wrong. Our answer is D. Inelastic kinetic energy is not conserved. Mathematically, we can absolutely go back and prove that. But we do know that because we're not dealing with atoms. Okay? On your assignment question, I do expect you to prove to me that this is what the equation is elastic or inelastic. Okay? Okay. So, ladies and gentlemen, I got practice problems for you there. Those are in your workbook. So if you guys could please do those. And then I've got more practice problems for you here. I've got 5 of them there. Now, the answers are just underneath. So these are all practice problems for you. All right? Okay. So reminder, at the end of this video, you have your assignment due. So get her done. And you also, if we are going to be in class once again, I have no idea what's happening. We are going to be back. We're going to have your unit test after this. All right? Alrighty, ladies and gentlemen, have a good rest of your day. No fires, injuries, or explosions. Talk to you later. Bye.